So we're going to try looking at this possible pattern. Let me show you a little program here. I'm going to imagine a region of space, if we can get the picture to show up, a region of space where we have a uniform electric and magnetic field. We say, well, that's not changing. But the region where there is this uniform electric and magnetic field is traveling through space. Okay. Now this is a little misleading. You might think that it looks like the arrows are actually moving, but you can think about there is a changing electric and magnetic field, because if I run this again, it's essentially going from 0 to some uniform value to 0 once again. So if I pick, for instance, some particular observation location, let's say right here, I'm measuring the E and B right here. Right now, E and B are 0, E and B are 0, E and B are 0, E and B are 0. E and B are non-zero for this amount of time, and then they go back to 0 again. Okay? So at that particular observation location, there was a change in the electric and magnetic fields, and same everywhere else, right? So we can think of this as sort of a slab of space. Okay, it's this slab of space where there is a uniform electric magnetic field is running into and out of the board. Okay, so it's extending this way. It's also going up and down, and it's traveling to the right at some speed. Okay, so this is the pattern. So imagine some region where we have electric field, and we've arranged it in its particular way. The electric field is pointing upward in the positive y direction. So that's E. And we have the magnetic field pointing out towards us. That's B in the positive z direction. And we're going to imagine this whole slab, okay, everywhere in this region of space that has some thickness to it, moving to the right with some particular speed. Okay? We're going to try plugging this into each of these 4 equations and seeing what we get. Okay? So we already know that if we don't have any electric and magnetic fields around, then the charge everywhere is going to be equal to 0. And there are no currents around. I is equal to 0. Okay? So let's start by plugging this region of field into Gauss's law, into the first of these 4 Maxwell's equations. And so here's a question. Here's our region of non-zero electric field. Okay? It's everywhere pointing in the positive y direction. And I imagine a box that is inside this region of electric field. Okay? And of course, n hat is always pointing toward the exterior and is perpendicular to the surfaces of the box. What's inside the box? Okay, well, let's see. We have most of us saying 0 net charge, but we just got done taking a test where Gauss's law was one of the topics. So let's see if we can apply what we know about Gauss's law to this situation. I'm imagining a box now, and maybe this isn't quite clear, but the electric field is extending essentially infinitely high and low in this slab. Okay, so I'm just picking some box that's inside this slab. And so I'm going to be measuring the electric field on this top surface, the electric field on the bottom surface, and the electric field on the sides. It's the same electric field everywhere over that surface. Okay? So what am I going to get? Let's look at the flux on each side. Okay? On the top, am I going to get a positive or a negative or 0 flux? Positive. On the front, what am I going to get? 0. On the back, left and right, what am I going to get on the bottom? Negative. Okay? And what do you know about if the magnitude of E is the same and the area is the same, then the top and bottom flux magnitude should be same. Okay, so when I add them up, I get 0. Okay, so what's inside the box? 0 charge. Okay, so let's think about what this is telling us. We said there are no charges around, so that's got to be 0. I just applied Gauss's law to this closed box, and I end up with 0. I get 0 is equal to 0. I say, okay, this pattern of fields satisfies Gauss's law. At least according to Gauss's law, this is possible. Okay? So that's done. Okay, we checked one off the list. We're going to go on to the next one. Okay? This wasn't meant to be that difficult. Is everybody okay with this? Got it? Okay. Well, the next one is Gauss's law for magnetism, and I don't think we even have to poll for this one, right? What's inside the box? Nothing, right? The net magnetic flux has to give you what? 0 over a closed surface. On the front, you get a what sign of flux? Positive, right? Because the magnetic field is pointing out towards us. On the back, it's negative. Everywhere else, it's 0, okay? And so, in fact, no matter what pattern of field we have for magnetic fields, we've got to get 0. And unfortunately, we do. So we get 0 equal to 0 for magnetic flux. Gauss's law for magnetism is checked off, okay? So far, so good. Now we got to think about the two that are more tricky, which are Ampere-Maxwell and Faraday's law. And let me erase some of this. And we're going to look at Faraday's law first. So let me just write it over here. Again, E dot delta L is equal to negative d dt of the magnetic flux through an area. So this is Faraday. And I'm going to write Ampere-Maxwell up here too. And since we already know that the current is 0 everywhere, I'm going to just write this as B dot dl equal to 0, no current, plus mu naught epsilon 0 time derivative of E dot n hat dA. Okay? So let's look at Faraday's law first. And what we're going to do is we're going to think about a loop, okay, because we have to think about the electric field around the loop. And the loop we're going to pick is a loop that extends partly into this slab of moving electric and magnetic fields and extends partly out of it. So here is the imaginary loop we're going to pick. It sort of juts into the loop. And so we have a region here where there is a magnetic flux, at least in part of that rectangular loop. Okay? So let's look at this in turn. So here's our slab of field. Here's the magnetic field pointing out towards us. Here's the electric field pointing up. And the whole thing is moving again to the right with speed v. We're going to call the part of so the loop has a width w and a height h. And the distance, the amount that's inside the non-zero field region is x. Okay? At this instant, what's the magnetic flux through the loop, through the bounded surface? Magnetic field is B. That's just a uniform magnetic field pointing out. We're just looking for the magnetic flux through that region. X is this distance. So imagine you just draw a rectangle, and part of that rectangle is sticking inside the region of non-zero field. Okay, how much of it x is sticking inside. Okay, and but the total distance from here to here is w. Okay. Okay, so we have 62% of us saying answer 4, b times x times h, right? Because the magnetic field is non-zero only in here. Outside, we said b is equal to 0. So when you're looking at the flux through this entire area, the only non-zero contribution you get to the flux is through this region, right? So that's x. That area is going to be x times h. Magnetic field is perpendicular to that area. The flux is b times x times h. Okay, so that's bxh. But for Faraday's law, we don't just care about the flux. We care about whether the flux is changing. So let's imagine that as this region of field moves, it moves a little bit, okay? So it starts here, and then it moves some distance delta x, and it's moving at a speed v, so that additional distance it moves is v times delta t. So in a time delta t, what's the change in magnetic flux? How much does the magnetic flux increase over that period of time delta t? Okay, big vote for number 3, which is B, V, delta T, H. Sizable vote for number 5. 5 isn't the change. What is 5? 5 is the total right now, okay? So our initial was B, X, H. Delta phi is going to be that amount of increase, which is going to be B times delta X times H, or B V delta T times H. And so phi final, we could say, is number 5. B times X plus delta X, or X plus V delta T, that total length now, times the height H. Okay, so we're just looking for the change, B V delta T times H. Everybody okay with the difference there? Questions? Okay. So Faraday's law, one way we could write it is that this side is the EMF, right? And this side is negative d magnetic flux dt. So if we want to find delta flux over delta t, what's that going to be? We're just worried about the magnitude for right now. We'll worry about the direction later. Okay, just divide that result by delta t, and you end up with B times V times H. Okay, so we end up with one half of this equation. So again, EMF equal to magnitude of EMF, just say, equal to delta flux over delta t, and this side is giving us B times V times H. All right. Well, let's look at the other side of the equation. The other side of the equation involves not flux, but this round trip path integral of the electric field. Okay, and we've done these before. You have a path, okay, a rectangle here. Inside this region, you have a uniform electric field pointing upward, but outside you have an electric field equal to 0. So think about picking a direction. Remember, around a path you have to go clockwise or counterclockwise. You can just choose clockwise if you like, if that makes life easier for you. And think about what the value of E dot delta L summed up over each piece of this path is going to give you round trip. Okay, and these path integrals always seem to drive us nuts, so let's talk about these once again. This is same thing as that one problem we did with Ampere's law. Okay, remember you had to break it up into pieces, think about the direction of delta L along each piece, and look at the dot product of the field and your delta L path vector. So let's look at each piece in turn. Okay, first of all, which way do you want to go? Clockwise, counterclockwise? You pick. Counterclockwise, fine. Okay, so we start here, let's say. We're going to go counterclockwise, so we have a delta L along this piece, but what's electric field out here? 0. Okay, so that gives us E dot dl is equal to 0. I go from here to here, but along that region, the electric field is 0. Okay, so again, the dot product gives me 0. I'm now inside the region. I'm going a distance of, well, be x plus delta x would be the total length. And the electric field is pointing in what direction? Up. So what's that dot product going to give me along that part of the path? 0. Okay, they're perpendicular to each other. I go downward, and that is a distance h. The electric field is pointing upward. That dot product is going to give me what? It's actually going to be what sign? Negative. Okay, so ignoring the sign, the magnitude is going to be what? EH. Okay, the electric field, it's going to be the magnitude of the field times the magnitude of the path length times the cosine of 180, okay, or negative 1, and then take the magnitude as just E times H. So far we've got EH contributed from this part. That part's going to give us what? 0. Again, the electric field is perpendicular to the path length. And again, if we're outside, the electric field is equal to 0. So we get 0. So the only part of this path that contributes anything to the path integral is this segment right here, and we get E times H. So we have E times H as our result on this side of the equation. And that tells us, just last question, well, I don't think we even have to poll. Shout it out. What's the relationship between E and B here? E equals BV. Okay, so the H cancels out, length cancels out, and we find a result here that says that if this is true, if this is a possible pattern of electric and magnetic field, then we've got to satisfy this relationship. The magnitude of the electric field has got to be equal to the magnitude of the magnetic field times the speed at which it's traveling. Okay? So let's hang on to that and do the very last equation here, which is this new thing, this Ampere-Maxwell law. I'm just going to run through it, but the basic idea is we do the exact same thing as we did for Faraday's law. I'm just going to choose a different orientation for my loop. And the way it's going to work is I'm going to choose a loop instead of, in fact, you can think of sort of rotating the picture. If I rotate the picture like this, so that the electric field is pointing out and the magnetic field is pointing down, I'm going to choose a loop that goes through the region that way. Okay, so imagine instead choosing a loop that's oriented in this plane, in the plane of perpendicular to the board here. And so if I just rotate the picture and draw E pointing out, and B pointing down, then I can go through the exact same reasoning. Okay, here's our slab again. I can go through the exact same reasoning using a loop oriented like that. Okay, so now I'm looking at the electric flux on this side and how it's changing, how it's related to the path integral of the magnetic field around the loop. So just by analogy, I'm going to have, this is again the width W, this is X, and it's moving a little bit, delta X, which is equal to V delta T. So I have a flux here, an electric flux through this region. And let me erase some of this. My phi electric now is going to be E times the area, or E times X times H. Okay. My delta phi is going to be E times that change in area, or E times delta X times H, which is E times V delta T times H. And the change in electric flux per unit time, I just divide out that time and I get E times V times H. Okay? So on this side of the equation, I get mu naught epsilon 0 E V H. On the other side of the equation, I have B dot delta L, and I do the exact same type of path integral again, right? Out here, the magnetic field is equal to 0. Along this part of the path, the magnetic field is perpendicular to the path, so I get 0. And then I go downward, and that's going to contribute what? BH, B times H. Okay, so this part of the path gives me B times H, and everywhere else again gives me 0. It's perpendicular here, it's 0 out here. So I end up with BH on this side of the equation, and once again the H cancels out. So I get another relationship. From applying Faraday's law, I get E is equal to B times V. Okay, so this comes from Faraday. Applying the Ampere-Maxwell law, I get B is equal to mu naught epsilon naught V times E. Well, let me look at these two equations and see if I can cancel some things out and see if I can solve for this V. Let me plug this equation into this one, and so I have E equal to mu naught epsilon naught V E times another factor of V, and then the electric field will cancel out, and I get 1 is equal to mu naught epsilon naught V squared, and I get V squared then is equal to 1 over mu naught epsilon naught, where V is equal to 1 over the square root of mu naught epsilon naught. Well, mu naught we know is 4 pi times 1 times 10 to the minus 7, and the units are Tesla meter per ampere. And epsilon naught is 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared. So here's what I want you to do. Everybody, take out a calculator. Grab a calculator, plug those numbers into this relationship, and calculate what V is. What do you get? You get the speed of light. You get 3 times 10 to the 8th meters per second. And that's no coincidence, because what is this traveling region of electric and magnetic fields? It's light. This is a pulse, essentially the simplest pulse of light you can have, just a constant pulse of traveling E and B. But this is light, electric, and so we call this electromagnetic radiation, and it was the triumph of Maxwell's theory that he showed that light was, in fact, this propagating disturbance in electric and magnetic fields. And we'll pick up with that next time.